Hello students, in this video we'll prove the argument principle. Let's suppose that F maps a region omega minus some poles P1 through Pn is a meromorphic function. Then, if C is a simple closed curve that encapsulates all the poles, every root of F and pole of F in its interior, then the integral over C, 1 over 2 pi I, of f prime of z over f of z, which of course is the logarithmic derivative of the function, right, is equal to the number of roots of f minus the number of poles of f. Beautiful. Okay. This is called the argument principle. Okay, excellent. So what's the setup? The setup is the following. So you have some region over here. Here's your omega. And of course you have roots. You have R1, R2, Rm, for example. There's m roots. And then you have poles, right? You have singularities over here. You have P1, P2, P3, and then Pn. And what the argument principle is saying is it's saying that and of course these might have, I'm assuming they're all simple, right? But of course you might have repetition. So R2 might be equal to R3, for example. R3 might be R4, et cetera, et cetera. And so that says that 1 over 2 pi I, the integral of the logarithmic derivative over this curve, is just the number of roots, m minus n, like that. Great. So how do we prove the argument principle? So the proof goes as follows. Here's the proof. So if z equals a is a root of f, then near a, f of z is going to be z minus a to some power k times g of z, where g is holomorphic and g of a is not equal to 0, right? That's how we express roots of holomorphic functions by the Taylor expansion. And that implies what? This implies that f prime of z over f of z near this point is going to be equal to what? Is going to be equal to, well, the derivative of this thing is just going to be k, z to the a minus k minus 1, so I have a k over z minus a plus g prime of z over g of z. And so that says what? That says that the residue of this logarithmic derivative at the point a is equal to k. So that says the residue of f prime of f at the point a over here at the root of that function is just equal to k, like that. Beautiful. Similarly, if f has a pole at z equals p, then what? Then f of z is some holomorphic function h of z over z minus p to the power, let's say, l, like that. Then by similar logarithmic differentiation, f prime of z over f of z near this pole point, the only difference is that this l is negative relative to that, right? So this is going to be negative l over z minus p plus the logarithmic derivative of h. And so that says the residue of f prime over f at the pole p is equal to negative L, right? Good. And so now I can just use the residue theorem, right? So by the residue theorem, by the residue theorem, 1 over 2 pi I, the integral over c of f prime of z over f of z dz is equal to, just the sum of the residues, I have the 2 pi over here, the sum over all the residues of f prime over f. Let's say at the zeros, so we'll say over the rj, j goes from what? From 1 to m, plus the sum of the poles over there, let's say j goes from 1 up to n this time, the residues of f prime over f at the pj's. Okay? Now, of course, at the roots, you get a positive contribution, so there's exactly m of these things, because I'm allowing for repetitions, m. And then at the poles, you get the negative signs. You have negative n over there. And that exactly proves the argument principle, right? So succinctly, what does it say? It says that if you are integrating the logarithmic derivative of the function, a meromorphic function, over a curve, and that curve encapsulates zeros and poles, then if you divide by 1 over 2 pi I, you're just summing up the total number of roots, assuming it's a simple curve, it only traverses those points once, right? In a counterclockwise fashion. And then every root gets a positive sign, every pole gets a negative sign, and that allows you to compute these integrals, the integrals of the logarithmic derivatives very quickly just by counting the roots and counting the optimal multiplicity, of course, counting the roots and counting the poles of these functions over here. Now, this may seem just like another application of the Cauchy theorem, but we're going to get a lot of leverage out of this because the zero counting mechanism or this pole counting mechanism, so in particular, where it's most often used for just a holomorphic function. If the function is holomorphic, that says the integral of the logarithmic derivative of a holomorphic function is just equal to the total number of zeros inside that curve of the function, right? So that's a particular corollary of this too. I can also make a slight modification of this. If I modify this ever so slightly and put in a h of z over here for another holomorphic function, you'll just be summing the holomorphic function over there at all the roots of the function f, right? So in other words, if you want to find an expression to sum a holomorphic function at roots of a different holomorphic function, you can use the argument principle. We'll see that illustrated in future videos. Thank you very much.